Okay, our Lewis structure example here, we have PO2 minus is the first one, so let's go through that one. We start out by drawing the skeleton structure, PO. Then we count our electrons and we keep track of that throughout the entire process. So P brings 5, each oxygen brings 6, and then we add 1 for a negative charge. That gives us 12 plus 5, 17 plus 1 is 18 electrons. And we've used 4 to do the skeleton structure, so 14 electrons left. Now we go to do the terminal atom. So we put 2, 4, 6, 8, 10, 12 electrons on the terminal atoms. That gets them to their full octet, or 8 electrons each. Now we look back to the central atom. So the central atom has 4 and needs 4 more electrons to get to an octet. We have 2 left, so we'll put that lone pair there on the central atom. And that is the point where we run out of electrons. When we run out of electrons, we're going to form multiple bonds using the lone pairs from the terminal atoms. That will let us keep octets on the terminal atoms, but get to a full octet on the central atom. So we go here, arbitrarily pick one of these lone pairs to use to form a multiple bond. So again, we'll take that lone pair off and turn it into a double bond. That then ensures that I get to an octet around each of my atoms here. And then at the last step, make sure to double check your work. There's really no reason to ever get a Lewis structure wrong in this class. You have tons of time on the quiz or the exam to double check your work and make sure you have octets and the correct numbers of electrons in each of your structures. So let's go through and do that. We want to check octets, 2, 4, 6, 8 electrons on the oxygen, 2, 4, 6, 8 electrons on the phosphorus, 2, 4, 6, 8 electrons on the oxygen. Then the total electrons, we said we needed 18 electrons, so let's check 2, 4, 6, 8, 10, 12, 14, 16, 18. We have all 18 electrons there. We can be sure this is a good Lewis structure. Our next step is doing the formal charges on each atom. Again, for that formal charge, it's the electrons that each atom brought, so the valence electrons that it brought to the structure, minus the electrons that we assigned to it, which, the easiest way to do that is by sort of thinking about that circle around each atom. So let's do that for the oxygen atom on the left here. I have the sort of circle I can draw around that oxygen atom. When I draw that circle, there's 2, 4, 6 electrons in the circle, and then remember each bond that I cross counts as 1 electron for oxygen, 1 for the phosphorus. So 2, 4, 6, and then 7 because I crossed 1 bond. So again, that just sort of counting the circle is the easiest way to do this. It brought 6, there's 7 in the circle, so that puts a minus charge on that oxygen. If I go to do the other oxygen atom over on the right, I still brought 6 electrons, but now in the circle, I have 2, 4, 5, 6 electrons in the circle, so that's a formal charge of 0. Then on the central phosphorus atom, again, I think about drawing that circle. 1, 2, 3 bonds plus the lone pair is 5 electrons in the circle. And phosphorus brought 5 electrons. That's another formal charge of 0. This gives us a third and final check that our Lewis structure is correct. Remember that the formal charge is going to add up to the overall charge because that's sort of what formal charge does. It's just a way to sort of count our electrons and keep track of them carefully. In this case, we have our minus charge here. There was an overall minus charge on this PO2 minus ion, so that does actually match up and check that we do have the correct Lewis structure. For CH₃CHCH₂, we have a skeleton structure that looks like this. We could go through and count all the electrons, but for these organic molecules, we can also just use the fact that each atom, in theory, will have a formal charge of 0 and use that to fill in any missing bonds. In this case, we can see that this carbon over here has its full octet, 8 electrons around it, making 4 bonds. This carbon here, though, is only making 3, And this carbon over here is also only making 3 bonds. So each of these are 2 electrons short of an octet. The normal state for carbon in one of these organic structures is to make 4 bonds. That will get it to a formal charge of 0. And so to fill out the structure, we can add a double bond here between the 2 carbons. That will get each atom to its octet. And again, if we check our formal charge, we have 4 minus 4 for the carbon on the left, 4 minus 4 for the carbon in the middle, 4 minus 4 for the carbon on the right. So all 0 formal charge. We have all of our 0 octets, or have all of our octets and duets on each atom. And so this is the correct Lewis structure. This second one, again, was sort of a little perplexing to me. Remember, for this sort of table, really almost everything you can write down literally just by knowing the steric number. So 9 out of these 12 boxes are just calculating the steric number and knowing the basic properties of each steric number according to VSEPR theory. So for a steric number of 2, you form 2 hybrid orbitals, that's sp. The electron geometry then is linear, because that's the best way to arrange 2 things. And the bond angle for linear is just 180. For 3 things, sp2 hybrids, and the electron geometry is going to be trigonal planar. That's the best way to arrange 3 things in space. The bond angles are a circle divided in 3, which is 120. For sp3, that's our steric number of 4, that's tetrahedral, happens to be the best way to arrange 4 things in space. The bond angles then, that magic tetrahedral angle of 109 degrees. For 5, we've run out of p orbitals, so now we start using d orbitals, sp3d. This is a trigonal bipyramidal basic geometry, and in that sort of structure, in 3D, that has 90 and 120 degree bond angles. Again, you can take a look at the 3D shape there for trigonal bipyramidal. You have sort of the plane, 3 things in the plane, and then 1 up and 1 down for trigonal bipyramidal. Then for 6, okay, now that we have that structure, let's go through and do our, compounds here, fill them in. Our steric number here on pH3 is 1 lone pair plus 3 bonded atoms is 4. That makes the electron pair arrangement tetrahedral. That makes the bond angles 109. And the central atom hybridization sp3. The molecular shape here, again, we sort of look at that basic tetrahedral geometry. The overall molecular shape then, there's 4 things around that central atom. So the central atom looks tetrahedral, but one of those 4 is a lone pair that we can't see. So what's left over here is just this sort of trigonal pyramidal shape. So the molecular shape is trigonal pyramidal. Then we go to the next one. There we have XCF4. The steric number is 4 bonded atoms plus 2 lone pairs is 6. That makes the electron pair arrangement octahedral. The bond angle is 90, and the central atom hybridization sp3d2. The molecular shape, we have 6 total things there, and 2 of those are lone pairs. Lone pairs stay as far apart as possible, so the lone pairs go above and below. Again, we've got sort of 6 things here, something that looks like this. The lone pairs go up and down. That leaves me with this final square planar geometry with just nothing above and below. So for the 6 occupied with fluorines, square planar molecular shape. Now we go to the last example here, O3. And here we have a steric number of 3, 2 bonded atoms plus 1 lone pair. That means our electron pair arrangement is trigonal planar. Our bond angles are 120, or really maybe a little bit less, but about 120, and the central atom hybridization is sp2. Okay, then molecular shape here. Again, it's three things around the central atom, but one is a lone pair. So if I sort of think about what that looks like, I have a trigonal type shape like this, but one of these is a lone pair. So the overall molecule here has this bent type of shape. Okay, for NNO here, drawing the possible Lewis structures, that starts from our same, correct procedure to draw Lewis structures. So we'll go through that. We have the skeleton. If we count our electrons, it's 5 plus 5 plus 6 is 16 electrons here. We've used 4 to do the skeleton, so we have 12 left. If we put lone pairs on each of the terminal atoms to get them to an octet, that uses our remaining 12 electrons, and now we have none left. So we now look at the central atom. For the central atom, it only has 4 electrons right now, but it needs to get to 8. We're out of electrons, so what that means is we're going to need to take 2 lone pairs from the terminal atoms and use them to form double bonds. So maybe I'll start by picking 1 from each, like this. But my different Lewis structures come from the fact that, again, I could have chosen to pick 2 from the light nitrogen on the left to make a triple bond, or I could have done a triple bond between the N and the O. So I'll just write out all 3 of those structures right now using that same procedure. If I take all 3 from the left nitrogen, then I would get a triple bond here and just 1 lone pair left over with 3 lone pairs on the oxygen. If I formed a triple bond over here, 3 lone pairs here, 1 lone pair there. Then again, my central one, I'll finish drawing that. Again, I have to remove those lone pairs and use them to form the multiple bonds. So double bond, double bond. And again, I should double check that I do have the correct number of electrons in these structures, 2, 4, 6, 8, 10, 12, 14, 16. I have 8 electrons around each atom, so that's good. And next, then I'm on to my formal charges here. So for formal charges, again, I'll go through sort of counting those electrons in the circle. For this nitrogen over here, it brought 5 electrons, and if I think about drawing that circle, I would put 5 electrons in there. That circle would pass through 3 bonds, so 3 plus the lone pair gives me 5. So that's a formal charge of 5 minus 5, or 0. On the central nitrogen, the circle passes through 4 bonds, so that gives me 5 valence electrons that it brought, minus 4 electrons in the circle for a plus formal charge on that nitrogen. And you can see that every time the central nitrogen has that same structure where it has 4 bonds, so all of my central nitrogens have a plus formal charge, because they're all going to be 5 minus 4 for a plus there. Then if I look at this oxygen on the right there, it brought 6, and the circle is going to contain the 6 lone pair electrons plus the 1 bond, so 7. So 6 minus 7 gives me a minus formal charge on the oxygen over there. Again, filling out the remaining formal charges. This nitrogen brought 5, but has 6 electrons around it. When I draw that circle in the circle, I would get a minus formal charge there. This oxygen brought 6, has 6 electrons in the circle, so a formal charge of 0. This one over here brought 5, but when I draw the circle, has 7 electrons in it, 6 lone pairs plus the bond. So this is a 2 minus formal charge. This one over here brought 5, has 5 electrons in the, or brought 6, has 5 electrons in the circle, so another plus there. Okay, now I can use the rules to, well, first let's use our rule down here. Formal charge always adds to the overall charge, so that's a check that we have correct Lewis structures. Plus 1 and minus 1 add to 0, plus minus 1 plus 1 add to 0, minus 2 plus plus adds to 0. So again, that just is a good double check that we have good Lewis structures here. Then which resonance structure contributes the most to the structure of the molecule? We'll go through our rules here. All formal charge equals 0 is best. Unfortunately, we don't have that here. Next, smaller formal charge is better. Plus or minus 1 better than plus or minus 2. So in this case, that will basically rule out our structure 3 over here. That has this minus 2 formal charge and 2 plus charges. So that's going to be worse than 1 and 2. So that's going to contribute the least. Next, we want, for 1 and 2, we have pretty good Lewis structures for both, a plus charge on nitrogen, and then in both cases, and then a negative formal charge on either the nitrogen or the oxygen. There we need to go to rule number 3, that the negative charge should be on the more electronegative atom if we have a choice. That'll make the resonance structure a bit better. So in this case, again, comparing N to O, the quiz had an electronegativity table on the back of it there for you, so you just compare the two. Nitrogen has an electronegativity of 3.0 on that chart. Oxygen on the chart has 3.5 electronegativity. So oxygen is more electronegative, and it is going to be the one that should have the negative charge. So that means structure 1 is the best. Okay, our other valence bond theory question here. Are pi bonds, each of this CN triple bond is 3 bonds, which are 2 pi and a sigma. So we get 2 pi bonds from this triple bond. Then we have 4 double bonds, 1, 2, 3, 4. Each of those contain 1 sigma and 1 pi. When we add all of those up, we get our 6 overall pi bonds in the molecule. Hybridization, this one over here, technically we might not view it as using hybrid orbitals. We could just use p orbitals here, but if we do treat it as sort of a central atom, we would give it a steric number of 2, which would give it sp hybrids. This one over here, we have to fill in our lone pairs to get everyone back to a formal charge of 0. And so this nitrogen over here is NH, something like this, where it's making 3 bonds plus having 1 lone pair. This H is bonded to the N, just in sort of a shorthand skeleton form here. So 3 bonds plus 1 lone pair gives us a steric number of 4, which is sp3 hybridization.